Good afternoon. I'm continuing with my discussion, very casual, unprepared, introduction, minimally, elementary, to general relativity and gravitation. Really gravitation, as we understand it. And elementary. Okay, elementary means it's composed of as few components as possible. Doesn't necessarily mean it's going to be easier. Actually, in this case, it is. I'm steering clear of topological spaces. I'm steering clear of differential forms. I'm steering, well, not exactly. I'm steering clear of metrics defined in terms of sets. We're just dealing with metrics in terms of distances on the Cartesian space or polar coordinates, whatever, and measurable distances. So, all right. We're dealing with the topics. Now, in the last lecture, I made a mistake. Kronecker delta, it's 1 when the indices are the same, and it's 0 if they're not. That was my mistake. I just wrote down this by mistake. It shouldn't be, it should be that. Okay? I do that. Make mistakes, they're not prepared. I have to figure out a way for you guys to write in. Okay, so here's the distance element. In two-dimensional space, it's just the same as infinitesimally close to the 2 points, let's say somewhere on a curve. The distance between them is given by Pythagoras' theorem. Now I just want you guys to get used to seeing what this looks like in matrix form. Multiply this by this and we take the dx and scan it down through here and I get dx dy. Take this guy here and scan it down through there and I get dx squared plus dy squared. And this is what I mean by the metric. This is actually a metric, but this is the metric tensor. We can make them bigger. Let's go to polars. In polar coordinates, the distant element, the differential distance element is the r squared plus r squared, the theta squared. Cartesians, polars. So in this case here, the metric tensor the metric tensor. We haven't said what a tensor is yet, we will. We're just working our way up to it slowly. Actually, let's do it in 3 dimensions. Let's do it in 4. So in 4 dimensions, that's what it looks like. Let's write the metric tensor. have the metric tensor for this particular case. And I just wrote it out. When I don't put in an element, it means it's 0. I won't always write them in. These are diagonal metrics. So yeah, I'll give you a look at that before I erase it. Now we want to transform from one type of coordinate set to another. Now here's a matrix transformation, and all it's saying is this. X dash is given by some function of x and y. But I'm going to write it a new way now. We'll just go subscript x equals x1, y equals x2, x dash equals x1 dash, y dash equals x2 dash. So therefore then, these things are functions of the x's and the y's. X dash is a function of x and y. In this case here, it's just a linear one. Y dash is x and a y in there too. Okay, for example, it could be a rotation. This matrix M could be a rotation. Okay? Now in that case here, determinant of M is cos times cos minus sine times minus sine, which is cos plus sine squared theta equals 1. So, for a rotation, the determinant of M, this transformation, is 1. Now, what this means is this. That's really what that line is saying. What else? Okay, in this case here, the inverse of the matrix is going to be, you can show it, is just the transpose of it. MIK is equal to MKI. Now to write the transpose, you just cos theta, sine theta, then minus sine theta, cos theta. So let's see what that is. Well, it's going to be this. Now this is all kind of elementary because if we were using our heads and didn't think too hard and thought a little bit about it, this is what we're doing. We take a point and we rotate the axis. Sorry, here's the point. By some angle theta. And then what we do is, that's the M. Now we rotate it back to the same place. So the net result has to be 1, right? Let's see. Sorry. So multiplying these two matrices, we get the following. Right now. These two guys here goes cos squared theta plus sine squared theta. All right. And the same for the lower one. Now for these ones here, the off-diagonal elements, let's take this here and go sine theta, cos theta, minus sine theta, cos theta, sorry, sine theta cos theta minus cos theta sine theta. And the other one is opposite. So what we've got in this case here is that the inverse brings us back to the same place, and that the determinant is 1, and the transpose of the matrix, okay, m times minus 1 gives me the identity. All right? And then what happens is this. What we get is the distance element hasn't been changed, so therefore the transformation is orthogonal. Orthogonal in a rough speaking way means that unit vectors are at right angles to each other. A transformation that's not orthogonal would be something like this. That wouldn't be orthogonal because we've changed the unit vectors to be not at right angles to each other. Now, orthogonal transformations preserve the length of vectors. And the interval length, and I'm going to start choosing because really what I'm doing is I'm just using 2 dimensions, but later I'm going to generalize to 4 it still preserves the new distance element. Where this is the metric tensor and it's diagonal. Or generally, G mu nu is not just 1, 1. There can be off-diagonal elements as well. That's what it looks like in 2 dimensions. Not orthogonal. So now we go back to our what we're talking about with regard to this metric, but we're going to use not matrix notation, we're going to use the Einstein summation convention and indices. Recall that we had this example in a previous case, and 1, 2, 3 is going to be 1 for the Levy-Chivy symbol, and -1 for this 1, 3, 2, where there's a non-permutation. Well, 1 refers to the index Lx. So therefore then the component of angular momentum in the I direction is given just by the ordinary cross product. But this is the way you find the cross products component by component. Okay? And this is easy enough to figure it out because you know the cross product is defined in terms of the determinant. This is the definition of a determinant. It's a permutation. Alright, so let's go on here now and remind ourselves of how we use this summation convention. We sum over indices that are repeated. I'm going to start using i's to be in 3 dimensions and mu's to be in 1, 2, 3 and 4 dimensions. I's, just 1, 2, 3, and the mu's will refer to 4 dimensions. And I'm going to write down a metric. Now this is a scalar. All the indices are saturated. The S squared is G mu nu times dx mu, and it looks like this. Sorry. Now, in 4 dimensions, we don't write these dx, dys, dzs, dt's anymore. We're going to write dx1. Oops. So no more dx, dy, dz, dt's. And this is our key result, our key quantity, which we're going to carry away all the time. Now, G mu nu is called the metric tensor. It's a tensor, and what does that mean? A tensor is an object that transforms in a special way. Let's see how that works. Scalar is a tensor of rank 0. Okay, so tensor of rank 0 will be a scalar. The gradient of this is a vector. This is a vector of rank 1. The G mu nu is a matrix. It's a 4 by 4. It's a tensor of rank 2. We will use the curvature tensor at some point. That will be a tensor of rank 4. Now suppose we have x as a function of the old coordinates. And in fact, every x, xi, we put dashes on these to make sure you know that they're new. Each one is a function of the old coordinates, which we're just going to write as, and we're just going to get rid of all these. We'll shorten our notation. X mu is a function of x mu, or x mu nu is a function of x mu old. Okay? Now we can show that dx mu by dx mu dash is the Kronecker delta. And similarly for that one here, I'll do that as a short example. I don't have time, YouTube is running out. I just want to get into the idea of why a vector is going to be a tensor of rank 1. The vector is seen in the new coordinate system. The dashed one compared to the older one, for example, x is also e.g. I'll leave it out. Don't have time. Okay, so transform Okay, we take the derivative and sum over the mu's. Which mu's? These mu's, because we're talking about a single mu, the dashed mu. Remember, you can't have three indices the same. This is a free index. So we might talk about the first component, summed over all of these guys. Sum from 1 to 4. Okay, so we're using the summation convention all the time, and eventually it'll get into your skull that that's the case. Now this is called a covariant vector. These are the covariant components of a mu dash. There's such a thing as a contravariant set of components. A quantity that transforms such as this is a covariant tensor of rank 1. Okay? Now there is such a thing as a covariant tensor of rank 1. If we use the inverse transformation, I'll show why that's the case in a minute. If the form of the transformation is as follows, a mu dash is equal to dx mu dash over dx mu with respect to dx mu times a mu summed over the mu's on the bottom, then it's said to be these are the contravariant components of the a mu, and we write them with the indices upstairs. And to get from one set to the other, we can go like this. They talk to each other. This is called raising and lowering indices. Now there's more we can say. this is a matrix with indices mu and mu dash. Okay? And this is also a matrix. We can show that one is the inverse of the other. Now, see, I'm out by a factor here. So I must have made a mistake here. I'll check up on that later. All right, never mind. I wanted to get the identity matrix. I may have made a mistake somewhere. Oh, yes. That's what I meant to do, actually. Okay, we have to stop it there. There are more technical things coming up, and then we can get away from it, and I'll talk about a little bit more physics, but some more physics on it. So we're doing some of the basics. Tensor calculus is a big deal. I'm sure there are lots of good books out. Actually, Shum Outline Series, Introduction to Vector Analysis, has a very short introduction to tensor calculus at the back of it. It would be a great one, okay? I would recommend that one. Avoid the big books like this one. Avoid it. Then there are abstract books like Wald, and there are lots of different things. We'll talk about that later.